welcome back. I'm just checking our video and audio, making sure that we have live stream up and running. How's that? Maybe the audio is a little better. Testing, testing. It does seem a little better. Okay, mute myself. Back into our computational mechanics. Now we're ramping up and we're getting into some data analysis. How do we describe data? How do we plot it? What are some stats? And then even this idea of like Monte Carlo modeling, that if we're dealing with random numbers, you can either use random numbers to kind of propagate error. So like we know that there's some error in our case, like in a radius. So what does that do to buckling loads? Or we can do something kind of opposite of like creating random numbers that calculate fixed values, like when we try to create pi with that. All right, so pulling up homework 2 to make sure I'm up and running. Okay, that seemed to work. So some things that I noticed as I was looking through homework 2. Seems like most people were able to use this head command. One thing that comes up is that if you're on Windows and you try to use this is called a bang operator. So it's getting you out of Python and out of your Jupyter notebook and into whatever's running behind the scenes. So in our case, we have a Linux machine that's like running Python for us. So if you're on Windows and you try to use bang head, like exclamation point head, it'll tell you that it doesn't exist. That's okay, just something, but this is the useful called bash command, the shell command. And the main thing that I like about doing this is when I import data, whether it's in a pandas data frame or it's in a NumPy array or however else I want to import it, I like to know like how many rows there are that make up the titles. I like to know, is it all the same? Like, is processor a number? And in this case, no, it's very much not a number. These are all strings separated by quotes. There are missing values. These NANs are missing. The date of introduction, it's not month, date, year format. It's just an integer saying what year it was. And then there's like the designer that we care about. Again, some kind of string in there. But that's the reason that I have you do that, is that it's good to know what am I dealing with? Like, what does this thing actually look like? And another thing that helps is, so if you're using here, if we come into like learning coach number 2, oh wait, module 2, that's weird. Date and semiconductor. So what is it called? The MOS transistor count. So if you get that head command, it's in a format that we can kind of read. We can look at this and figure out what it is, but it's in a very good format for a computer to read. So this one is taking each of them and actually turning it into into a string and then like turning it into a data frame, and that's okay. Because now it'll show me like, okay, now that I have that CSV file, I can look at transistor count and then make a plot that way. But this is rather than, because another way that I could have done this was actually download, like find this file, download it, upload it back into Copilot, and then ask it to do something for me, when all I really need to know is like, how do I access this stuff? Like, how do I get this column, the date of introduction column? How do I get that column? And in this case for pandas, it's kind of easy. Well, it's not easy, but it's easier than trying to figure out like, is it column 1, 2, 3, 4? But that's the nice part about pandas, is that. All right, so then this one, oh, actually, let me grab, here, I'm gonna fade to black for a second. I'll be right back because I just wanted to grab somebody's plot from the homework. Rectangular, copy that. And okay, welcome back. So let me zoom out some so we can see the whole plot. So a lot of people got to this point where you have this ABV versus IBU plot, and the question was like, what differences did you notice? And people are like, oh, and there's lots of different answers. So things like, oh, they're skewed, or things moved, or the axes are different. But what does the plot show you? Like what was different? And this is a skill that I'm hoping we keep working on as we keep working through this. Let's get down here. Let's copy this one, paste it in right next to it. So here is the plot that you did in the homework. Here's the plot from the reading. And you're right, like things changed. This max value was 70, this one is 100. So one way that, if I'm trying to make an actual comparison between this plot and that plot, my first step would be, all right, well then this one needs to start at 0 and needs to go to 0.11, and this one and up here this should start at 0 and go up to 100, and then I can say, look, everything shifted down. Even the max dot up here, the highest one up here, went from 90 something down to 70 something. So everything shifted. This big yellow dot is at 50. Now it's down. Now it actually moved up, right? This big yellow one, it decreased. I think it decreased. Let's see, 0.07. Yeah, so ABV, it looks like alcohol by volume is probably about the same. Again, it would help to put them both on the same actual axes, but down here it's 70 and up here it's 50, so it dropped that IBU by 25 units. But that's kind of the analysis that I'm looking for here, is like, if you noticed a difference, how do you actually describe that as an engineer trying to talk to other engineers? It's not a skill that comes easy, and it's hard, but that's why we're practicing here. But I wanted to give an example of, if you're noticing something different, then how do you actually quantitatively describe it? Other big thing is that there's all these dots along the x-axis, and I think some people kind of noticed those but didn't, I don't know if there was a thought of like, oh, maybe it used to be something else and it shifted down. My guess, based on what we did with the data, is that these were not included at all in this original plot. They were completely ignored, like especially this one, way over here at 0, because these are all non-alcoholic beers. And for the most part, non-alcoholic beers are not measured. They're not given IBU units. So I think we're capturing, maybe we're not getting good data, but we're capturing more of the data. Like we're able to actually look at more styles of beer because we're replacing IBU missing with IBU equals 0. Anyway, that's just something that I thought I would share. All right, so now, this one, let's do this. Yeah, because this is one that people usually kind of struggle with, and I'm trying to think, should I start with, let's try it. I'm gonna copy this into our learning coach and see what information it gave me, what information it gives us. So let's make a new one. Module 2. I must have had a typo there. I'm trying to answer this question. Okay, so first it shows me how to load this thing into a data frame. I already knew how to do that, so I'm not even gonna bother copying that code in. Let me zoom in a little bit. Because yeah, I knew how to do this, so I can load it in, and now I've got that information. And let's see what it tells me to do next. So now it's doing kind of the process that I would have done, at least the way that I had thought about it and the way that I've done it in the past, is create a data frame that is just one designer's worth of data. So that's what this one is saying. Like, give me all the data frame of the times when data frame designer equals this designer, where this designer is a unique list of all the designers that are in my list of things here. And you know what? We can try copying this in. Let's see what happens. Oh, and it just called it DF. I don't like that. I just don't like it. Because I called it Tran. And I already loaded in matplotlib. And creating, this was one thing that people were asking about, like, oh, how do I use scatterplot to make this? But semilog y creates you can create a scatterplot just by saying like, oh, use circles. If you want to connect the dots, you can use a line like that, or you can connect them with like dashed lines or dash dot lines or dash dot dash. There's all sorts of options. So let's see. I don't like this title either. Designer, transistor, count, growth since 1970. And some people probably notice this, like when you first put on this legend, it throws it on top of your data. So let's tell it move the legend outside my plot. Yeah, this is the code that we want. We don't really need that location upper left, but that's okay. We can do it. See, and I don't think that location upper left is doing anything, because if I remove it, it's still in the same place. Because if I say bbox to anchor, that is telling it what the location is. I never liked this command, and I think I've looked up how to use it at least 500 times. It's one of the first things that pop up on my Google search is like, how do I move a legend in matplotlib, because I moved them so many times. Then the other thing that we can do if we want, if this is, I mean, there's a few things we can keep going from here, right? Like there's it's like doing data visualization is its own art form. Like you can get really into it and make really beautiful plots. To start, it helps to just like get a plot, like just, all right, what does this data look like? And so let's ask it again. So now we'll say, make the legend box 3 columns wide. And there's this parameter called ncol in that legend box. Where is it? This one. So I can add that to my own down here. And now it's starting to look pretty good, right? Now that I see like all of these things, there's a pattern to the colors. Blue, red, yellow, green, gray, purple. Blue, red, yellow. So it's not like giving me new color, like ARM and Garrett Research and Intersil and Acorn, they're all blue dots. There's different ways that you can kind of start separating out that data. Let me show one way, because I can change like markers, right? So I could say like, okay, put everything as a square. That doesn't help much because it's still the same colors, but I could have squares and colors, and that would help, right? So what if I just create like a marker list bracket I, where I'll just keep changing I. I'll set it equal to 0 to start, and then after I plot something, I'll say I plus equal 1, and then it'll go to the next marker. Actually, do I want to go backwards? It's a good question, now that I'm thinking about it. Let's see. So X is bracket 0, 1, 2, X -1. So you can go forward or backward in list. -2, -3. Oh, you can still go out of range. Okay, so then what we could do is 1% len of X. Oh yeah, we should print it, right? So I'm just doing a little bit of debugging, and this is the power of using an interpreter like this. And I could keep asking AI for this, but I just get annoyed with how AI, it's like, hey, do all this extra stuff, like even this little thing of like, hey, throw the location in the upper left. It's like, but I already bboxed to anchored this thing. Like I manually said, go to this location. Why would I also tell it go to this like nondescript location? So anyway, so I'm going back and forth between AI and like just troubleshooting this way. So if I have X is 0, 1, 2, index 0, 0, 1 is 1, 2 is 2. I'm just trying to go through 10 values and see, can I get those values 0, 1, 2 to pop up over and over? And sure enough, I get 0, 1, 2. I don't get 3 though, because that goes back to 0. Or if I do // 1, 2, that one's not bad. Oh, yeah, so I do want oh yeah, 0, 1, 2, right? 0, 1, and 2. Oh my goodness. Yeah. So that's fine. So, and even if I had a 3 in there, it would go 0, 1, 2, 3, 0, 1, 2, 3. Okay, so that's what I could do here if I get a list of all the markers. So now I'll jump back into, and I could look up, I could Google what are all the markers for Python, but I want to say, give me a list of all of, let's say 10 different markers in matplotlib plots. So it's showing me like the different things, but output the list as a Python list that I can use in my code. So now I can grab this. So these are 10 different markers, and I could ask for more, but 10 is a good start. And I'll go back into homework 0. And I'll say marker list of I percent len of marker. I like marker list rather than markers. And now, let's see, I was trying to see if any of these line up. Every company has its own color and marker. And now, without dealing with like color maps or anything like that, I've made distinct markers for every company in here. And I could go look for more markers and try something else. If I want to kind of see what the trends are for everything, maybe I would also want to say, like, give it lines to connect it. So let's say line width equals 2. Oh, I guess what I could do is just add a dash in here. I'm just holding Control and clicking through and adding a dash on all those. And now I could see like, all right, when did these companies start and stop creating these things? Actually, let me say like marker size equals, I like to do at least like 15, just make them a little, well, 15 is too big, right? Let's go 10. That's a little better. But like these orange dots for Intel. Intel started in the 70s. It's still making chips to today. Meanwhile, these stars are ARM. Oh, I'm surprised. ARM. I guess ARM mostly does smaller chips, but I feel like they're making new ones. I'm surprised that they're not out here. But anyway, Garrett Research, I think, is only that one, only has like one dot somewhere in there. There's one square dot up here for Amazon. Like, I think they only created one thing. All right, cool. So I wanted to show that, and you could keep changing this. You could change like what color scale you want to use, like what colors, and you could do that same thing of like, you could choose what list of colors you have, and if you had like an odd, if you have prime numbers, kind of like if you have 7 different markers and 11 different colors, then you could cycle through and they won't line up until 77, until the 77th one, right? All right, cool. Okay, so now let's get into some predictive. So we have some data, we can measure it, we can visualize it. Let's get into some predictive results here. And that's what this one, so I'm gonna say first step was just grabbing the US energy data. So I'm gonna say that it's energy of energy bracket, I think entity equal United States, kind of like that. It always helps to double check your results. There we go. So that looks right. I have 1965 through the year 2018 of data. Cool. And now EU is going to look exactly the same, but this is going to say Europe, like this, EU. And there we go. It worked. There's also this code that the code works for, you can put in USA to get this first one, but there's no code for Europe because it's a collection of countries, not an individual country. Meanwhile, United States is one country. Okay, cool. So now I want like this EU primary, and this is, so I'm showing you like my like process here a little bit. You can do it in a different order. Like at the end of the day, we'll probably have the same code telling us the same information. But I like to walk through how I approach this and kind of talk out loud or think out loud as I'm doing it. So my first step is like, if I want to do a fit of year and energy consumption and compare the US and the EU, first thing I want to do is just plot the data, like what, yeah, and that's what I'm asking you to do. And the reason I ask you to do that is that it makes sense to me to just plot it. So plot this EU of the year versus EU of the primary energy, and I'm gonna do red squares for that one. And then I want to do the same plot for the US. Ooh. But I want to do blue circles for that one. And I like to say, I like to increase my marker size. So I've got these markers, they're kind of going along. For the most part, energy use has been increasing. I don't know which is which, so maybe it would help to have a label. Well, I mean, I do, because this is blue for US, but it never hurts to have a label, right? So USA and EU, there's the dots, and they're moving along. US has more energy use recently than EU. That kind of tracks. All right, now that I have this plot, I can say, all right, what is the average slope? Like, what is the best fit curve for this blue line and for this red line? And it's a comparative thing. So we're using US and EU to compare, like, what are energy uses on both sides of the Atlantic Ocean for kind of these first world country places. So let's do a US fit is going to be polyfit of US year, US primary energy consumption. The order of the fit is a first order fit. EU, and you know what, let's copy and paste this since we're doing the same thing twice, and we'll just grab these, change that to EU. And I saw some people get to this point. Technically, I've done the fit. Like the work for getting a fit is done, but these numbers are completely meaningless until I see them on a graph. And I made this comment on a lot of homeworks of like, you can't say that this is the best fit plot unless you show me that it's the best fit plot. And the best way to do that is by plotting data and the fit together. So since I'm trying to plot this stuff, like I already went through the effort of making this plot, I'm gonna copy it down here. I'm gonna use, since I used polyfit to make this fit, I'm gonna use polyval to evaluate the fit. So I need, my x-axis is exactly the same, but my y-axis is going to be np.polyval of US fit. And the inputs are going to be US my bracket year. And let's put this as a blue solid line. And I'll copy this since it's going to be the same, but I'm going to have a EU, and now I want this to be a red line, and it would help to label these, right? So here's the US, it's straight line kind of like this. The EU fit is also a straight line. And from these two, at least from these two fits, it looks like the US and the EU have been steadily increasing their energy use and at the same slope, right? And that is what this one told us. Like 2 versus 1.996, or I guess 200 versus 199.6 terawatt hours per year. That's what that first term is. This second term is telling us what the intercept is. And that one's kind of a nonsense term because in the year 0, I don't think we were, as the US, putting 3.76, so what is that? 0.4 thousand terawatt hours into the earth. That it just doesn't make sense, because we were still using energy. We weren't using much. And so one of the nice things about using polyfit is like, all right, yeah, sure, this straight line seems to generally capture it. It's like, well, I could try something bigger, right? If I wanted to say, well, it's not a first order fit, maybe it's a third order. Maybe this is a third order, like a cubic polynomial. And when I run it, now I can see it's still kind of weird. Like there's a lot of stuff happening that does not get captured by my curve, but maybe it's a little bit, like especially for the European Union, it does seem to follow that data a little bit better. For the US, not so much, but anyway, I like polyfit for that reason, because you can quickly change your analysis. And we'll revisit curve fitting in the linear algebra work, because we'll look at kind of how does curve fitting actually work, like what is the definition of a least squares curve fit. Cool. All right, so then the next step was trying to split this data, of saying like, all right, this line doesn't quite fit anything on here. Like it kind of fits in the middle a little bit, but there's a bunch of other stuff happening. So maybe we should split the data and say 1990 or 1984 or something, or 1980. Maybe there was like things were happening on one trend for a while, but things happened differently after that. 1990 seems to be when things changed, or 1980, something like that. So I'm going to copy this, or I can hit like edit, copy cell, and then paste cell below. Now I have 2 copies of the same thing. I still want to do polyfits, but the only difference is going to be like, we'll say pre, and post. And we'll call this US pre. And the first few times you see this, it looks a little weird, but let's walk through like how this kind of works. So the US is a data frame. It goes from 4,761 of our original data frame all the way to 4,814. If I say US of year more than 1965, or sorry, more than 1980, some people, at least the first time I saw it, I expected like, okay, well, it's going to give me everything after that, but it doesn't. What it gives me is a list of true and false statements. So it was false up until the year 1979, and then at this level, at this point, it becomes true. Boolean, if I have a list of Booleans like this, I can use that list of Booleans to index this data frame. I can also use it to index NumPy arrays. It's called Boolean indexing, or slicing, like we're slicing things with Booleans, true and false statements. So I'm going to ask for US of this Boolean. So I'm plugging in this whole list of true and false. Well, really, it's a data frame. It's a data frame full of only true and false statements that is the same size as this thing. And I get 1981. Oh, so yeah, I forgot. I said 1979, but I didn't use a more than equal to. Maybe I will, just so I can. Yeah, so I'll grab that 1980, and it's showing me all the data since then. This is going to be my US post data. And my US pre-data is going to be less than. And rather than counting 1980 twice, I'll just count it the one time. And sorry, I didn't mean to jump around like that. Post and pre, like that. So I'm using my fit, creating two fits, a pre and post poly fit, and then evaluating it with polyval in these two cases. I'm just leaving the label the same in this case, but that's okay. Now I can see this US fit goes up, then there's a break, and now it starts following kind of the same curve that it had before. But it was much faster increase before. And I can do the same thing with Europe, same kind of process. Oh, with this, so this one is also like a predictive kind of thing. So let's do this one kind of quick. And let's put these as like squares. So I didn't see this as much. I guess it doesn't come up as much now that we have like an AI assistant, but if you do a best fit curve on the log of data, then you try to plot that best fit curve. So I evaluate that curve. I haven't put it back into a log scale, so it's going to look tiny. And it's like, well, what happened? I thought it was supposed to fit my data. And again, this is why you always plot your best fit curve, because if this is your prediction that every transistor in the history of computers has always been over 1,000 transistors per semiconductor, and you're predicting 90 to 150, something is very wrong. So the missing piece here was that I have to bring it back. I have to take the exponent to bring it back into that log scale. There's also, I saw some people like changing what log scale they're using. Like I could say a log base 2, and then I would just have like a 2 to the thing. So if I take the log of my data and do a best fit, that's great, because now it takes that logarithm style stuff and puts it onto a linear plot. I just need to bring it, I need to get the actual values of my plot back into that 2 to the something. So all right, so we'll leave it in this log base 2. Log base 2, is that what I want? We'll try it. We'll do log base 2. You can do it however you want, whether it's natural logarithm, log base 10, however you want. But I have a curve. It seems to go through most of the data. It seems to be the best fit curve for this data. And it does look like a linear, it does look like things were increasing on a straight line on this semi-log Y plot. Gordon Moore predicted that every 2 years, the transistor count would double. Is that what my plot is showing? And I saw lots of different answers here. Some people were kind of like, oh, look, the line goes through the data, so Gordon Moore was right, or no, he was wrong. So let's take a look at my 2 coefficients. One of them is 0.4845, so 0.485. The other one is negative 9.4. Again, this intercept is kind of nonsense, and we only really care. And again, it goes from like highest order to lowest order. That's always how this polyfit works. So this one's kind of nonsense. It's saying that in the year 0, there were negative 900 transistors on every semiconductor. It's like, well, year 0, we didn't start making them until the 70s. So yeah, that we could call 1970 year 0, and then it would just be that number. Okay, so this is the number really that I care about, is the slope of this curve on this log scale. Is this right? Let's do a little bit of math. So if my transistor count equals 2 to the A times T plus B, then transistor count of T plus 2 is 2 to the A times T plus 2 plus B. All right, easy enough. It's supposed to double. So that's supposed to be, when I go from time t to time t plus 2, it should be twice as much. So if I take 2a of t plus 2 plus b divided by 2a t plus 2, plus b, this is equal to 2at minus at. This is some fancy logarithm and exponent sort of math, right? If I have 2 squared divided by 2 to the 1, it's 2 squared, 2 to the 2 minus 1, so 2. Same thing, at minus at plus a2 plus b minus b, or overall 2 to the 2a. All right, so 2 to the 2a, what is that? And let's put it in parentheses so I don't have to worry about order of operations, right? So according to my best fit, based on the historical data from 1970 to 2020, the rate that transistors doubled, every 2 years, it didn't double, it was 1.96 times whatever it was 2 years ago. That's the average growth across this whole thing. You could go through, like, maybe you think these are outliers in the data, like they lie pretty far outside the normal ranges in here. So you could say, like, all right, well, I shouldn't include those, maybe it should be closer. But this was, so the error here, so print Gordon's error was 2 . So he was off by a factor of 0.042, which is not bad. We're on a log scale, so that adds up to a lot over time, but this line is very close to a slope of 2. So it's not that it's wrong. And maybe if you did take out these outliers, it would be a lot closer. But that's one way to do this. And if I was dealing with exponents, it would be the same thing. I could say, like, e to the 2a is the double. Like, I could have done this whole thing with it. I could replace the 2 with an e. And then that would tell me, like, how close I was to doubling every year. But that's one way. And again, try practicing it, because it's a hard skill to have, but try to practice, like, how do I say something specific and measurable about these questions that I'm being asked. They're intentionally open to let you, like, kind of play around with it and try it out. All right, now we're getting into some cool Monte Carlo work. So let's take a look at the random walk. So some people, oh, it's all in one thing. I was wondering why people were doing that. I'm just adding a new cell right here so I can do this Monte Carlo estimation. So I saw some people, it seemed like some people were trying to use the learning coach for this. So let's see what happens there. Oh yeah, it's over here. I want to make a new trying to answer this question for Buffon's needle calculation of pi. And there, let's see what it gives us. Because it seemed like I saw some stuff that did seem like, yeah, so random.uniform. This works. I'll copy that in. So my x values are going to go from 0 to 1. I don't like hard coding this. I like to use variables in here. And uniform works, or actually, yeah, I don't really like np.random now that I'm saying this. I like to do this from numpy.random import default rng equals default rng. I usually give it a seed number, and that's for reproducibility. So these are pseudo random numbers. If you give it a seed, you'll get the same random numbers each time. And as you run it, you'll get new random numbers. But you can think of it as like, if the computer has a deck of cards, if you ask for RNG 42, it will arrange the cards in a certain order, and you'll always get the same order of cards. So as you won't always get the same operation, because if you do things out of order, it'll change, or if you run something and then come back, it'll change. But I do this, I like to set a seed value that way, and now I can say rng dot and rng dot. That one, if you look at NumPy documentation, default RNG is the highly recommended way of using random number generators. There is legacy. I mean, there's legacy code that maintains this np.random work, but default RNG is the new way to do things. Okay, so then we're calculating. Yeah, that's weird. So I saw some people saying like taking a factor of 1/2 in here. And it seems like sometimes it used the 1/2, other times it didn't. But we'll grab that. Let's see how it works. So X values, and now this is where I saw most people come up with a problem. So we'll grab this code. And let's estimate that pi. Yeah, and sure enough, pi is 5.13, which is not right by any stretch. It's not even remotely right. And the reason for this is that, oh my god, n. I like to use n, so that if I increase n, it changes everywhere. Because the bigger the n value, the closer I should get to the actual value of pi. So here at 10,000, I'm not getting any closer to pi. And why is this happening? So the reason is that I'm creating angles from 0 to 360. When the angle is anything more than 90 degrees, that means my get a new one of these. Undo that. Let's undo that. So let's say this is my needle. That's my theta I. This is my xi location. If the angle is anything more than this 90 degrees and less than that 270 degrees, then the min that I'm saying this is x min and that one's x max, they get reversed. The x min is no longer the x min. It's the x max. It's over on the other side as I spin that thing around. So I need something to take care of that. There's more than one way to do it. Logical and is taking care of this first case, like when those things are true. So what do we want to do? We could look at sign changes between the two, and that's one way. or we could string together a logical and a logical or statement. So crosses line, let's say case 1. And then we'll say crosses line case 2 is going to be when this is more than 0, but this one is less than 0. And let's just make 10 of these. For I in range n, print x end min I max I crosses line 1 I crosses line 2 I. And yeah, that's okay. We can leave it like that. So what I've done here is I've created 2 true and false statements. One is the case. So here, this is our first case. The min is less than 0, max is more than 0, so it's true. It crosses the line for case 1. Meanwhile, in this one, min is more than 0, but max is less than 0. So before, I was not catching that. It was still false, but now it's true. So I've got true, false, false, true, false, false, true, false, false. There's never a case when both of them are true. I think even if I made this a billion, you can't have a case where both of them are true. But what I can do now is create so there's a logical and, but there's also a logical or. And the logical or is telling me if both of them are false, then this is false. If one is true and the other is false, this is true. If this is true, that's false, it's true. True, false, true, false, true, true, right? So this, now I'm getting to the point where this is what I want, right? The crosses line where I create 2 logical and statements and then a logical or statement to actually filter out, like, is it crossing that line? So I'll run this, calculate pi. Now, even with just 10 needles, I'm at 3.3, which is a lot closer than we were at 5. And if I go up to 100, I'm gonna hide these debugging steps. It actually gets a little worse. So let's go to 1000. 3.13 now. Now I'm getting pretty close. And if I change this seed, then we'll get closer or further away. Main thing is that the bigger n gets, the closer, the more we'll converge to the actual value of pi. And yeah, so, and again, I'm kind of thinking out loud as I go through this about the way I approach this. But this is the thing that I noticed for a lot of people. I guess the learning coach was sort of steering you down that path of like, okay, yes, this is counting when it crosses, but only half of the time. So I guess technically you could just take that ratio, multiply by 2, and hope that symmetry is at play here. And then random walk, it seemed, if you do want some more help with this, you can reach out, or we could start like a GitHub discussion about that. But that one I didn't see too much trouble with, like a few people. But this was where a lot of people started to have some trouble, where this is an example of propagating error through an equation. So I have an exact equation where the critical buckling load is always this result, at least for this kind of structure. But the problem is the radius keeps changing. Like as I keep installing more support rods, each rod is going to have a radius with either, it could be 0.01, it could be 1 centimeter, or it could be 0.9 centimeters or 0.95 centimeters. So there's uncertainty in one of my variables, even though I have a very certain equation. And that part's kind of weird. But this equation itself doesn't tell me anything about what the critical length is. Like I can't use this equation to calculate critical length. I have to just use this, calculate critical loads, and compare that to the actual load on the structure. So I have 1,000 kilograms held up with 100 rods. So 100 steel rods holding 1,000 kilograms. So the total load is 98.1 newtons. First step is let's just finish out this this function. And I'm just copying that in so I don't. So I need np.pi to the third times e times r to the fourth divided by 16 divided by L squared So I'm taking just that equation, plugging it into a Python function. So it's the same thing as if I was just like plugging this into a calculator. Like if I know what R is, I can calculate what that critical load is. Now I need to generate what is R. Like it's a random variable, and I want it to have a mean of some value, and I want it to have a standard deviation of some other value. So I'll say R is RNG normal with the location. Wait, is it normal? Now I gotta RNG dot normal. If I could spell, yeah, location. What? Why was it telling me something else? All right, so location is R mean, scale is R standard deviation, size is N. So N rods. And here I have an example of like a default length, and I can plug in default values here too. 0.001, 0.01, and what we had steel, right? 200E9. Yeah, 200E9. Then technically I should move L to the beginning since I'm going to be changing L, or I could just give it a default value. Let's call it L equals 5. And I like to separate it down onto multiple rows like this. and let's try it out. So Monte Carlo buckle gives me a mean load of 164 newtons and standard deviation of 61. It'll change each time I run it, again, because we're generating random numbers, and each time the computer is kind of like dealing out these new random numbers for me. But what does this mean? And if the changing is bothering you, we can make this number as big as we want it. And the bigger we make it, the less it's going to change, because it's, again, like converging. Similar to how time step, as we were decreasing time steps for Euler integration, it started always giving us the same result. Same thing here. The more numbers we use to make this calculation, the less the mean and the standard deviation would change. The Monte Carlo, you converge with more random numbers. So what is this telling me? 164 with standard deviation 65. That is, and again, we have 1,000 kilograms times 9.81 divided by 100 rods. This number is much bigger than that number, and even this number minus that number is still bigger than this. So it seems like this structure is fine. Like the average load is bigger than the applied load. We should be good to go. But here we have this request that only 2.5% can fail. So how many, so if this is my mean and that's my standard deviation, how many would fail in that case? Let's see. Do we have some normal distributions in here? Distribution plots. A little bit. Not really what I was looking for. All right. Normal distribution, percents. So for a normal distribution, 68% of the data is within one standard deviation of the mean. If you go 2 standard deviations out, now you're talking that 68 plus this 17, so 95%. So 95% is within 2 standard deviations if it's a normal distribution. So one thing we can do is say we started with a normal distribution, we plugged it into a function, let's assume that it's a normal distribution, and we can go on our merry way and say yes, that is the case. So if that's the case, so here's my mean, there's my standard deviation, and they're equal to that. So lower 2-5 limit so the lower limit, that 2.5% of these P critical loads that I just calculated is 33.7 newtons. That's a much different number than this 98.1, right? Like we're saying that if I go 2 standard deviations away, I'm down here at 33 newtons, which is much lower. So really I want this number to match that number. So let's copy it and change this L. Let's make it 2 meters, make it much smaller. The shorter something is, the less likely it is to buckle. Now it's 211, so I way overshot. This thing is way too short now, because now there's probably only a 0.1% chance that anything will buckle. Meanwhile, there's 100 rods and 2 to 3 of them can buckle and everything's fine. So 2 is too short. 4 is now like 52, so that's too long still. 3 right in the middle, I could say like maybe 3.5. Too much, 3.2. Sorry, which way am I going? 3.05, like that. All right, so 2 around, somewhere around 3. And what I was doing was just literally guessing and checking. We'll look into better methods for guessing and checking for numerical methods, but it works. And when you have a problem like this, it's called an inverse problem, where if I have the result, if I have all the inputs, I know how to calculate the output. But if I know the output, there's no way to like invert this function and solve for this value. Like it can't be done. I know there's a formula and technically you can go in there and jam it into the wrong side, but it doesn't work because we have this random variable kind of stuck in there, and that's just how it goes. We can't use this result and that equation to say this is the new L. So that's one way. Another way is, let's look a little deeper at what this PCR is. So let's output it. If I want to know, like, what does that P critical load look like? And I should run this. Typo. So it's telling me like, hey, PCR is not defined. I'm like, I'm defining it right there, but it was because in this return statement, this PCR is actually that PCR here and here. Just, again, give you a little bit of the Python debugging kind of work. Okay, so PCR. If I look at a histogram, and I've got a bunch of values here, so I'm going to split it up into 100. I'll just, if there's a whole bunch of outputs after something, you can put a semicolon and hide it all. All right, now I can look a little bit deeper at this data and see this curve is not a normal distribution curve. It's actually skewed over to the right, which means the mean and the mode are not the same value. Print PCR dot mean. No mode? There's no mode? Wait, what? NumPy, calculate mode. Stats.mode? .unique. Anyway, yeah. But mean is 165. It's like somewhere over here, but the peak over here, the mode, is somewhere in this range. So it's different. This thing is skewed. But I could use this to say, like, all right, well, PCR less than 98.1. Divided by that. And the number of So in this curve, the number of these there's a whole bunch of rods that are like 100, whatever, 110 to 200 Newton buckling load, but there's a whole bunch that are less than 100. And it actually makes up 13.9%. That's what I'm looking at here. So if I don't want that, so that's what I'm starting with, is that if my mean is 164, and my standard deviation was that, then that's the output there. If I don't want that, then I could change this, or let's just copy it, paste it, and let's merge these two. And now we will copy paste. So I have two copies. I have the original where L is 5, and I don't want that lower limit anymore. I want to know how many are actually less than that P critical here. And I don't have, I can print out that mean and mode, mean and standard deviation. So if I make the length 4, I'm down to like 2.2%. And it's the same thing, right? Each time, because I have so many, N is so big that that's a pretty good number to count on. So I can actually increase it. I can make it like 4.5. Well, 4, maybe 4.1 or something. 4.09, 2.6, getting pretty close, right? There's some randomness to it. Really, I want it to be less than 3, more than 2%. And yeah, now, so this is a little bit better. It's less this is a more conservative method. If I assume that it's a normal distribution, it works out to be a lot more conservative in this case than doing it where I actually look at what is the histogram, like how many of these rods will buckle at a given load. So 98.1 or less, or less than, yeah, do less than 2.5, 2.6-ish. Cool. Hopefully that helps as you're like thinking about numerical methods and these homeworks, and now we're jumping into the project to do for Monday and Tuesday. And yeah, it's been a pleasure working on, like, seeing your work through this, and I look forward to